Hello everyone, I am Manuel, and in this presentation I will talk about our paper named 360 3D photos from a single 360 input image. This is work in collaboration with Richardt. It is only a matter of time that virtual reality settles as default medium to consume digital content. One critical property of VR is that of immersion. To feel truly immersed, we need visual content that surrounds us with 360 degrees and can be experienced with 6 degrees of freedom. This means that we can rotate and translate our head freely in space to explore new angles and perspectives of the world. 360 content is typically created either through modeling in scenes or capturing 360 images, both with pros and cons. Modeling operates in a series of stages to create the final immersive scene. Conceptualization, a 3D modeling stage to give a structure to the scene. Textures and materials that provide the looks of the world. The design of the lighting. Although models provide high flexibility of design and naturally provide 6 degrees of freedom, the design process is expensive and requires multiple levels of expertise to obtain the final product. On the other side, 360 images require just a camera to capture the scene. However, they can only be looked at with 3 degrees of freedom, hindering total immersion. Therefore, our goal is to make 360 images fully immersive. 360 images surround the viewer in a scene, are easy to capture with current devices such as smartphones or 360 cameras, and have a low memory footprint as they are stored in the same format as conventional images. A 360 image can be looked at through a viewport by placing a virtual pinhole camera that simulates our head. The virtual camera can freely rotate around a fixed point, focusing on different regions of the surrounding 360 image. But what if we not only rotate our head but also shift it in different directions? Moving our head results in distorted renderings that are not natural, as shown in the middle. Also, as shown in this frame, occluded content behind the flower vase is revealed in the ground truth. However, this is not the case when rendering directly the 360 image. So why is this? Well, 360 images come with limitations. They are ultimately flat and lack depth cues, such as motion parallax, which is essential for humans to perceive 3 dimensions. A 360 image represents an observation from a single viewpoint, and we cannot know what lies behind when translating our head. As a result, a 360 image only provides 3 degrees of freedom. Therefore, our motivation is to transform 360 images into what we name 360 3D photos that provide 6 degrees of freedom, both rotational and translational, with depth cues such as motion parallax and monocular disparity. For this, we design a pipeline to create 360 3D photos. The pipeline is composed of 2 stages, an initialization stage and a refinement stage. Let's focus on the first stage. We use Gaussian splats as a scene representation. Gaussian splats need a set of initial pinhole cameras for being trained. From the single spherical input, we first predict its depth, and then we extract perspective views corresponding to the faces of an icosahedron. The process is illustrated as following. We place a virtual pinhole camera at the center of the sphere and rotate it in discrete rotations that correspond to the center of the face of the icosahedron. We repeat this process, and we end up with 20 RGBD images with known camera parameters. From this pool of views, we train our initial Gaussian splats. As you can see, the input or the 360 image is not a texture sphere anymore, but it has geometry due to the depth supervision that we impose during training. The optimized Gaussian splats naturally provides motion parallax. However, changes of viewpoint reveal previously occluded regions that appear empty, shown as black holes in this image. Therefore, we need to fill these gaps with plausible content to create a complete scene. The second part of our pipeline consists exactly on this. We rasterize the point cloud at a novel viewpoint, inpaint the gaps, and add new Gaussians into the holes so that the representation is aware of new content. This is done repeatedly until we fill these occlusion gaps inside an action sphere. So how do we sample new views? We sample new views inside an action sphere surrounding the initial viewpoint, where the user is expected to move. This action sphere is typically 50 centimeters of radius. The resulting images have holes and need inpainting. How do we perform inpainting? From the Gaussian splats, we can render RGB images and a transparency mask that indicates the empty regions. These two images are fed into stable diffusion, inpainting model, and the result is a new image with new content inside holes and identical content to the input outside the holes. Then, the inpainted image is fed to a monocular depth estimator to predict its depth. And now we have a new RGBD pair for the novel viewpoint. We need now to make sure that our Gaussian splats are aware of inpainted content, so that when querying additional novel views, they used previously filled content. Note that inpainting is done in 2D. We can spawn new Gaussians at the holes with the information of the RGBD pair we just computed. However, these Gaussians are initialized only in position, but need optimization of other properties such as scales, rotations, and opacities. Therefore, what we do is we take these raw Gaussians and we add them to the initial Gaussian splats. At the same time, we take the pair of RGBD inpainted inputs and we add them to the initial pool of views, and we keep training for further iterations. Eventually, the properties of Gaussians at the holes converge and we are ready to query a new view. In these results, we show our method and two other baselines. As you can see, our method better preserves the original content of the 360 image and produces more plausible results in the occluded regions compared with other methods. In conclusion, with the proposed method, we bypass the expensive modeling stages. Our scene representation dynamically refines occluded areas as new views become available, adding a multi-view consistency to the partial scene. The final representation provides 6 degrees of freedom from a single 360 image. And finally, we achieve state-of-the-art in image quality and perceptual video quality at 100 FPS per megapixel. We believe this is the first step to upgrade 360 images to 6 degrees of freedom experiences at VR rates. Thank you for your time.